Hello and welcome. My name is Elhelw. Today we will continue to talk about cardinality estimation, which we have started in the previous video. We talked about the query optimizer, and as part of the cost-based optimization, the optimizer has to estimate the cost of each operation in each of the candidate plans. And this cost estimation happens by using a cost model, which is a collection of cost functions for each operation, which uses different information such as the cardinality, the input and output cardinality of the operation to estimate the cost. So then we started talking about how do we estimate this cardinality. The cardinality is the number of rows. The optimizer uses different statistics that is stored and maintained in the system to come up with that cardinality estimate. The statistics include number of rows in each table, things like number of distinct values, most common values or most frequent values in a column with their frequencies, and also things like histograms if those are available. And we have seen how to use that information to estimate the output cardinality of the selection operation, for example, which has filters. So in order to do that, we had to estimate the selectivity of the filter, which is the ratio of the rows that satisfy the filter, and then use that to estimate the output cardinality. I will link the previous video in the description as well as up here on the screen. So please take a look at that before you continue with this video, since there's a lot of information that we will use in this video as well. Today we will continue talking about cardinality estimation for other operations. So after talking about selection in the last video, today we're going to talk about aggregation and join. So let's jump ahead and talk about aggregation first. So aggregation, as you all know, is the operation where you apply some operation on multiple rows, and you want to summarize those to one row, or sometimes you have grouping, sometimes you don't have grouping. The simplest version of an aggregation is when you don't have a group by. So something like looks like this. Select count star, for example, from employee. You don't have a group by in this case, so this means just summarize all of the table into a single row. So whenever we have a query like this is the plan. We know that the output cardinality is going to be 1. So regardless of how many rows are input to the table or to the query, it's always going to have just a single output row. So estimation of the output cardinality here is very simple. The more interesting case is when you have a group by, right? If you have something like this where you're grouping by department ID, for example, then in this case, we don't have just a single row, we have multiple rows. This operation basically would split the rows into different groups and then summarize each group into one row. So it will look something like this. In this particular case, it estimated the number of output rows to be 20, even though the input rows was 5,000. So how did it get that estimate, right? This is what we want to know. So for a query with a group by, let's look at the plan. The plan looks something simple like this: a table scan followed by the group by aggregation. Let's say the table scan has 8,000 rows. Then what is the number of rows coming out of the group by? The number of rows coming out of the group by is the number of groups based on whatever you're grouping by. So in this example, we're grouping by the category column, right? So for each category value, that's a separate group, and then we're going to count the numbers in that group because we have count star and output that. So for each group, we have one output row. So the number of output rows is the number of groups, and the number of groups is the number of distinct category values. So we can use the number of distinct values of the category column to estimate the output cardinality in this case. And this is a piece of information that we have used in the past. We have used that when we were estimating the selectivity of a filter. So we can also use that same statistic to estimate the number of groups for aggregation. What happens if we're grouping by multiple columns? This is also a very common thing to do in queries. Here we're grouping by category and supplier. Ideally, so basically what we want here is the number of groups, right? Like we agreed that when you have a group by, the number of groups is the number of output rows because we have a single row per group. What is the number of groups here? For each combination of category value and supplier value, you have one group. So basically we want to get the number of different combinations between categories and suppliers, right? But most likely we don't have that information. What information do we have? We have the number of rows. We also have number of distinct values for the category column. We have the number of distinct values in the supplier column. how do we get the number of combinations of categories and suppliers, right? As we have said before, whenever we are missing some information, we have to make some assumptions. So what assumption we can make here? We can assume that the category and the supplier column are independent. So based on that assumption, we can say that the number of possible combinations is basically the product of the number of distinct values in both columns. So we can say that because we have 10 different categories, 20 different suppliers, then there is 200 possible different combinations of category and supplier values. So this will give us an estimate of the number of groups in this case. So because we assumed independence, we can come up with this value. So if we try to generalize this, if we have group by column 1, column 2, all the way to column n, and we want to estimate the output cardinality, given that we have the input cardinality and we also have the number of distinct values for each column separately. So we can say that the output cardinality is the product of the distinct values of each of these columns. Of course, that number of rows cannot exceed the input cardinality, right? Because when you're grouping, you're not creating new rows. You're just compressing or compacting the existing rows into a smaller number of rows. So this is why we have to add like a safeguard here that the output row is actually the minimum of the input rows and the product of the distinct values. So again, to repeat, we are doing this assuming that these columns are independent. Of course, this is not always true. Like in the example of category and supplier, it might be the case that, let's say, the category kitchen doesn't have all the combinations of all the suppliers. Let's say you might have the kitchen products coming from just a single supplier. So that independence assumption doesn't always hold, but because we don't have any better information, that's all we can do. There could also be interaction between group by as well as a filter. So here we have a where filter, where category equals kitchen, and then we're grouping by the supplier. And again, we have the same information. We have the number of rows, we have the number of distinct values in each of these columns. So how does this work? Assume that the plan looks like this. The table scan, the output cardinality will be the number of rows in the table. Now we have a selection assuming uniformity because we don't have any better information, because we have 50 distinct values in the category column. We're going to assume that each of these values exist equally. So since we're selecting only one value, category equal kitchen, this should be in 1/50 of the rows, which is only 10 rows. So this is the estimate for the output of the selection. And then on top of that, we have the grouping. We're grouping by supplier. There are 30 different supplier values, so we will say that we have 30 groups, right? But because the input cardinality here is 10, so there is no way that we're going to get more than 10 groups. So the maximum that we can get would be 10 groups in this case. So this is how you can estimate and how different operations can interact with each other. All right, now let's talk about the join. Join is one of the most common operations in SQL queries. Specifically, I'm going to talk about inner join, not outer join or any other kind of join. So inner join obviously is most commonly used. The idea is you have a join between two inputs using some columns from each side. And let's say you have some input cardinality 300, 2000 from both sides. So now we want to estimate the output number of rows from the join. The simplest case is when you have a join between two tables that have a primary key, foreign key relationship, right? Why is that simple? Let's look at this example. We're joining employee and department on the department number. And this is what the tables look like. So in the employee table, you have an employee number as a primary key, and then you have a department number as a foreign key that's pointing at the department table. In the department table, obviously, the department number is the primary key. So how many rows are going to be produced by the join of these two tables, right? If you look at the department table first, is every row going to be in the output? No, there are some departments that don't have any employees. For example, department number 10 doesn't have any employees, so that is not going to be part of the output. It's not joining with anything. So some departments may not be producing any outputs. So trying to get the number of rows based on the department table is not going to be easy. But let's look at the employee table. The employee table, each row there matches with one department because you have the department ID. So each row matches with exactly one department. So each row in the employee is going to produce an output. There is no row that has no match because it's a foreign key. It's guaranteed to be one of the department values. So for each row in the employee, you're going to produce one output row. So the number of output rows basically is the same as the number of the rows in the employee table in this case. Of course, if you have any filters, you're going to have to apply the selectivity of those filters as well. But in the absence of filters, the output rows is going to be equal to the rows on the employee side, which is basically the rows coming from the side that has the foreign key. So let's look at this example. We have that same query pretty much, and this is the plan. And you can see here the estimate of the join is the same as the number of rows coming from the employee table, as we have explained. And again, if you have any filters, then those will start to have an effect as well. Now, this was the simple case, the foreign key primary case. Let's look at the general case where you don't have that relationship. If you want to join tables S and T based on some column A and columns B on both sides, right? Now, what we want to estimate is the number of output rows, right? The number of output rows depends on the values on both sides and how many rows match with each other. Let's look at a single value for now. Let's assume that there is a single value 5 that exists in both columns. It appears in, let's say, 2 rows in table S, and it also appears in 3 rows in table T. So based on this particular value, how many output rows are going to contain this value? Is going to be, those 2 rows coming from table S are going to match with the 3 rows from table T. So basically all the combination of those. So it's going to be 6 output rows. So these are the output rows based on this single value. If we can get that for every value in the table, then we can add these up and come up with the estimate for the join output, right? All right, so let's start again. What information do we have? Suppose that we have the number of rows in each table, and we have also the number of distinct values in the join columns. Let's put some numbers as an example. Assume that table S has 200 rows, table T has 1,000 rows, and then the column S.A has 20 distinct values, and T.B has 25 distinct values. How do we get from there to the estimate that we want? Let's see together. Let's assume that, or let's try to get how many rows exist on both sides for a given value. Since this is all the information that we have, we're going to have assume uniformity as we've done before in the past. So because we have the number of rows and we have the number of distinct values, we can estimate roughly how many rows contain the same value. So we're going to say for a given value, the number of rows on S with that same value is going to be equal to the number of rows total divided by the number of distinct values. So it's going to give us 10. Again, because we have 200 rows and we have 20 values, so we're going to assume that each value exists in 10 rows. So just dividing. Again, because we assumed it's uniform. We're going to do the same thing for table T or for column T.B. because we have 1,000 rows and 25 distinct values. So we're going to assume that each of these values appears equally. So each of these values appears in 40 rows. So these are assumptions. Of course, again, they might not be accurate, but this is the best we can do given this information. Now, okay, so we decided that each value appears 10 times on the S side and each value appears 40 times on the T side. So assuming that the values include or there's inclusion there, so we can apply the equation that's on the left side to get the number of output rows for a given value. So the number of output rows is going to be the product of these two. So basically it's going to be 400 for a given value because it appears 10 times here and it appears 40 times here. So all the combination is going to give us 400 output rows per distinct value. All right. So how many different values do we have in the output, right? That's the other part that's missing. The number of output values, to get that, we have to look at the inputs. So in the inputs, we have 20 coming from one side and 25 coming from the other side. Again, we're going to assume inclusion. We're assuming that the least of the two is going to join on the other side. So you have to have 20 coming from here, 25 coming from here. We assume that all those 20 different values are going to join. And then the other side has some 5 extra values that are not matching anything. So the assumption here is that the minimum of these two values is going to be the number of distinct values in the output, which is 20. So we have estimated that we're going to have 20 distinct values, and each of these values appears in 400 rows. So now we can multiply these two, and that will give us 8,000 rows, and this is the formula for it. You can write it in different ways. So yeah, given those assumptions and these estimates, we've estimated that the output cardinality here is 8,000 rows. So inputs is 200 and 1,000 rows from both sides of the join, and then the output is 8,000. Again, remember that here we don't have any filters. If you do have filters, then we have to estimate the selectivity of those filters and then apply that to scale down the number of rows that we have. All right, now we've estimated that using only the number of rows as well as the number of distinct values. What if we have additional information? Like what? Let's start from the information that we have seen already again. So number of rows or number of distinct values. Now suppose that we, in addition to that, we also have histograms. We've seen histograms in the past. Histogram is basically a collection of buckets. Each bucket has a start and an end, like a boundaries. And also each bucket has a frequency, or the ratio of the rows that exist within this bucket. Of course, the frequencies have to add up to 1 across the histogram, 1 meaning like 100%. And this represents the distribution of the data of this particular column. So how can we use histograms to estimate the join cardinality, right? First of all, let's try to scale the number of rows and the number of distinct values to each bucket. So looking at the number of rows, if we have 200 rows in table S, right? And column S.A has the frequencies in the histogram. So we can say that each of these buckets has a percentage of the number of rows. So we can basically multiply the number of rows by each of these frequencies to get the number of rows within each bucket. And we can do the same thing with the number of distinct values as well. So doing that will give us an estimate of the number of rows and number of distinct values within each of the buckets. So I just wrote it here for the first bucket, but it applies to all of the buckets. We also know the boundaries of the buckets. Like even though they're not shown on the screen, those will be, the boundaries of each bucket will be stored as part of the histogram. All right, so now we have the number of rows and number of distinct values within each bucket for the S.A histogram. We can do the same thing for the histogram on T.B if we have that histogram as well. So, of course, there is no guarantee that the two histograms are aligned. They don't need to have the first, like the same beginning or the same end or even the same buckets. Like the bucket boundaries can be different, as we can see here on the screen. So if we want to use these histograms to estimate the join cardinality, we have to align the histograms. What does that mean? It means that we have to make sure that the buckets have the same boundaries on both sides. So we need to insert new boundaries. By inserting new boundaries, this means that we're going to split some of the existing buckets into multiple buckets. So as an example, let's insert a boundary here corresponding to the one in T.B. So we're adding a boundary to the S.A histogram. Adding the boundary means splitting the first bucket into two buckets. So as we split it, we also have to split the number of rows and the number of distinct values. And we're going to split them assuming that the data inside that bucket is uniform. So based on where we're splitting it, the ratio of that split based on the bucket size and where that lies in the bucket, we're going to split the number of rows and number of distinct values accordingly. So in this case, for example, we're going to end up with 60 rows in the first part and 20 in the second part, 6 distinct values in the first part and 2 in the second part, depending on where the split is with regards to the boundaries of the bucket. So we're going to do that for every single extra boundary that we insert. So we're going to insert another boundary here and there, which aligns with the boundaries in the lower histogram. And again, each time we do that, we have to split an existing bucket into 2 buckets or sometimes more. We're going to do the same thing for the other histogram as well. We're going to split that other histogram based on the boundaries of the first histogram. So in the end, we're going to end up with 2 histograms with the same boundaries. Sure, there might be some differences like in the beginning or the ending, as we can see here. So the part that doesn't exist in both histograms, these are parts that are not going to join because they don't match on both sides, so we can ignore these parts. So the parts that have corresponding buckets in both histograms, these are the parts that are going to match through the join. So for each pair of corresponding buckets, right, we have, for each bucket, we have the number of rows and we have the number of distinct values. So if we look at the first corresponding pair of buckets, for example, we can use the same formula that we used a few minutes ago, just on this two buckets, right? Just substitute with the number of rows and the number of distinct values, and you will get the number of output rows based on these two corresponding buckets. Now repeat that for every pair of corresponding buckets on this histogram and add these results up, and you will get the number of output rows total of the join. As you can see, it's not an easy process. It's computationally expensive process. Of course, the more buckets that we have, the more expensive this becomes. This is why we have to make sure that the histograms that we store are not super huge. But even though, again, this is computationally somewhat expensive, but the optimizer has to do this as fast as possible because it has to do this for hundreds or thousands of plans, so it needs to be super fast. So what happens if we're joining multiple tables, not just two? If we're joining 3 or 4 or 5 tables, right? The same thing we do with the actual data, right? Like we join 2 of them, estimate the output for that, use that as an input to the second join. We're using the estimate that we got as an input to get another estimate, and so on and so on and so on. Of course, the more we do that, the estimates that we have here are not accurate, right? Like we start with accurate estimates from the statistics, and we come up with an estimate using some assumptions, using some approximations. So the estimate is usually less accurate than the original statistics. Now, when you use that estimate as an input to another join, the new estimate is going to be even less accurate. So the more joins that you have, those estimates get worse and worse and worse with larger estimation errors. This is just like a byproduct of that estimation process. It's a known problem. Like the more joins that you have, the larger queries, the estimates tend to get worse along the plan. We can see that as an example here. If you have this query with 3 tables being joined, so this means that you're going to have 2 join operations. Here's the plan. And I used explain analyze, not just explain. So this means that we get the estimates, but we also run the query and get the actual runtime information. So let's look at the joins. The first join, like the lower join in the plan, it estimated the output rows to be 8, but when it actually ran the query, it only got 5 rows. So there's an estimation error there. The upper join, like the second join, again, it estimated 2,000 rows, but then the actual number of rows that was produced was 1,264. So a larger error happened here. So yeah, the more joins that we have, this error tends to grow, and at some point the estimate becomes like completely off. Just something to keep in mind. All right, so this is basically what I wanted to talk about today. So let's summarize quickly before we wrap up. So yeah, today we continue talking about cardinality estimation, specifically about estimating the cardinality of aggregation as well as join. For aggregation, we saw that if you don't have a group by, then the cardinality is 1 row. If you have a group by, then you use the number of distinct values in the grouping column to estimate the number of groups, which is the output number of rows. If you're grouping by multiple columns, we assume independence and we multiply the number of distinct values, of course, not to exceed the input cardinality. We then talked about join cardinality. The simple case is when you have a primary key to foreign key join, in which case the number of output rows is the same as the number of columns coming, same as the number of rows coming from the foreign key side of the join. In the general case, we saw how we can use our statistics, such as the number of rows in each table, number of distinct values, histograms, all that information together in order to come up with the join cardinality. We also saw that we have to, as we have done in the past video, we have to use some assumptions like independence, like uniformity, like inclusion, in order to be able to utilize the statistics that we have to estimate the cardinality. And of course, these assumptions introduce errors. And the more joins or the more operations that we have in the query, these errors start getting bigger and bigger. So this is just the nature of cardinality estimation. I hope the video was useful, and I hope it was not super difficult. This is one of the most important parts of query optimization. And if you have any questions, or if anything was not super clear, please let me know in the comments, and I will try to respond as soon as possible. Please like the video if you thought it was useful. Hit that like button. Subscribe to the channel if you have not already. And with that, thank you so much for watching, and I will see you in the next video.